So hi, I'm happy to be here talking about a little bit of work we've been doing trying to incorporate electrostatics in DEM modeling, specifically with the LIGHTS DEM package. Most of this work was done by the two folks that are highlighted in bold, Hao Wang and Jay Phillips, who are grad students at the University of Central Florida. Hao is actually now in Hawaii. She just graduated as a postdoc in Hawaii. And this is preaching to the choir, but lunar dust is complex, and we understand that it has both dynamic and electrostatic interactions, and can be charged both naturally and due to interactions with humans, with rovers, all sorts of different processes. And so one of the challenges in understanding those interactions is figuring out the best way to model them. And there are lots of different techniques, obviously, that are used for this modeling. One of which is DEM, discrete element method modeling, which really looks at granular scale mechanics and is used for can be used for pretty complex granular interactions. And so efforts to account for electrostatic interactions in these DEM models will improve modeling and help us understand behavior of these really interesting environments. A couple of photos here just of a landing cloud, a cloud of dust kicked up due to landing on one of the Apollo missions in the top right, and one of the lunar roving vehicles kicking up dust as it drove around on the lunar surface, because these are both applications for where these models might be applied. So just really quickly, and there's a lot more detail about the LIGHTS DEM and other publications and talks, but LIGHTS is mostly focuses on mechanical and thermal interactions of particles. It's actually built off of a code called LAMPS that looks at atomic scale interactions. And so LAMPS in itself had a lot of electrostatic interactions, but those weren't incorporated at the grain scale mechanics used for LIGHTS. So one of the things what we're trying to do is work those back in a computationally efficient and effective manner. The two sort of cases that we're going to be types of interactions we're looking at are both short and long range interactions. The two that are italicized, the gravitational interactions and the contact forces, are both already included in the LIGHTS distribution as you download it. And so I won't talk about those at all today, but those are obviously important and we use them. But then there are additional long range interactions due to Coulomb forces. So this is in the presence of an electric field or a plasma, and due to charged grains themselves. And then also conduction and tribocharging that are short range forces that generally require contact. And some of this work has been presented by Jay Phillips at the ASCE Earth and Space Conference, and it's the paper that came out of that. And Hao Wang's paper is in revision and should be published in ASR shortly. So I'm going to go through a few different test cases we've done to validate implementation of these different types of forces in our models. So the first one is just looking at Coulomb screening. So if we were looking at electrostatic interactions, and I don't know if this laser works, but the equation is up in the top right if you would like to look at it. But we're looking at long range forces. So if you have charges on grains and an electric field in the environment, they will interact with each other, and we want to look at the effect of those forces due to those grains on each other. So the screening parameter we can implement looks at if you have a large distribution of particles, so you have a big cloud of dust particles and they're all interacting, there's going to be some sort of fall off of effect due to grains that are farther away versus the grains that are closer. And the screening parameter is a way to sort of parameterize that and not have to calculate all of the interactions between all of the grains in the cloud. It sort of gives you a cutoff to say grains that are this far away we're going to be able to ignore because their relative forces are small in comparison, which is really important in numerical computations to improve efficiency. And so the kappa parameter there is this Coulomb screening, and you can see that, so we're plotted here the initial force between grains as a function of time. And then the force as a function of time to contact. So basically, as you increase the kappa parameter, the initial force decreases, you see less of the forces between the grains, and it takes then longer. If you start 2 grains far away from each other. So this is two grains that are charged. If you start them farther away from each other, as you increase that screening parameter, it's harder for them to see each other, so they take longer to come into contact. So you're effectively sort of screening those forces from each other. So you can play with this parameter to see how long it takes for them to feel each other. We also have implemented a sort of basic conduction model. I'm not going to talk too much about this one, but basically if two grains come into contact, they can exchange charge. And this is one of the cases we evaluated, where you had two differently sized grains that had different charges on them. As they come into contact, those charges equilibrate between the grains, and we see that it works as we implemented it. Again, this is a very basic version of this model. Conduction and how this works with true grains is complicated. One of the limitations of all of the things I'm going to talk about right now is that these are spheres, and charging on spheres is treated in this model currently as just like a representation of the charge distributed on the grain as sort of like in the central point of the grain. So being able to distribute charge on the surface is still something we're working on. That requires implementation of multi-sphere models or more complex geometries. But the basic contact and conduction does work. So the more interesting cases we've been exploring are what happens when you have tribocharging. So tribocharging is another contact force interaction where you have grains touching each other, whether they're of unlike or like work functions, so the same materials or different materials. They can exchange charge. This can be due to rubbing and different types of contact forces. So we implemented a model from Laurenti et al., a 2013 paper, where they had also done a tribocharging model in a different DEM. So we implemented a similar model in ours. And here on the right, we show the results of those implementations compared to on the top, compared to their simulations, and on the bottom, compared to the experiments. So this model is that there are two different types of basically plastic spheres that are sort of getting charged up in a hopper. And you can see that over time, there are two different plastic materials. So one charges more positively, one charges more negatively as they exchange charge in these interactions. And our implementation in lights on the bottom, you can see actually matches very well to the experiments, and actually matches better than their implementation in their DEM to the experiments. So that's a great sign for us that we're pretty accurately accounting for how tribocharging interactions may occur. And then we get to some actual sort of physical cases where we start to try to explore charging in a lunar dust environment. And so these are lunar-like cases. So the particles are relatively large compared to what a lot of we think of for lunar dust, but they are sizes that might be lofted in different interactions. So this is a case where we start with particles that start at some height above the surface, and they have an initial charges on them that are randomly distributed about 0. So you have some positive, some negatively charged particles, and they fall due to gravity on the lunar surface and in the presence of an upward pointing electric field. So the interesting thing we see here is that you have these particles that sort of all start at one point, and they charge and interact with each other, both with these physical interactions and these long-range interactions. And this causes their charge to change, which also changes their velocities and where they're going to end up on the surface. So you can see here we have a case of the black dot right in the center is what happens if you have all of your particles that are uncharged falling. They just fall straight down. But if you apply a charge on the particles, they will actually distribute in a radius around the central point.
2 minutes left.
Okay. And we can see that differently here. So this is another plot of the final positions and then the velocities. So final position on the left, velocities on the right in the X, Y, and Z directions. And you can see a little bit better here that you do get dispersion in all of the different axes due to the charging on the grains. So this is important to implement in charged particle cases. So it's showing that this is important to implement charged particles in these cases where we're trying to understand if dust gets kicked up by a rover wheel or something like that, where is it going to go? And so I'm actually just going to skip to my summary slide in interest of time. So this work is ongoing. We have these basic implementations. We're going to start exploring more complex cases of more lunar-like interactions, potentially going to smaller grain sizes and doing larger numbers of grains. And this will be informed by knowledge of what plume interactions might look like and what these wheel interactions might look like. So thank you.